Take a look at this algebraic logarithm problem. When students see quadratic expressions inside both the base and the argument, they prepare for a long grinding path of factoring equations. But stop right there. Before we write down a single line of algebra, let's run an essential 20-second structural knowledge check. Look directly at the base of this logarithm, which is 10x squared minus 17x plus 7. Most aspirants will carefully set this greater than 0, but completely miss the hidden constraint that completely invalidates a log base. What single rational value forces the base to equal exactly 1 and destroys your entire domain calculation? If you can isolate that hidden point right now, you won't fall into the paper setter's bracket trap. Let's decode it.
Hey thinkers, welcome back to Think Sharp Alley, where every turn leads to a smart solution.
A log function has 3 rigid pillars. That means for any logarithmic function to be defined, 3 strict mathematical rules must be satisfied simultaneously. First, the argument must be positive. Second, the base must be positive. But the base can never equal 1, and that's our third point. Let's unpack them one by one. First part, the argument condition. Here the argument is 18x squared minus 11x plus 1, which needs to be greater than 0. Now splitting the middle term to factor the quadratic, we get this. Then using the wavy-curve method, the critical points are clearly 1 by 9 and 1 by 2, and we need the region where x is positive, that is minus infinity to 1 by 9 and half to infinity. Please note, here none of the boundary points are included in the solution. So this forms our first condition. Now the second part, the base positivity condition, where the base is 10x squared minus 17x plus 7 must be positive. Again factoring by splitting the middle term, we get 10x minus 7 into x minus 1 greater than 0. Here the critical points are 7 by 10 and 1. We need the regions where x is positive, so which is clearly minus infinity to 7 by 10 and 1 to infinity. Now this forms our second condition. Third is the base unity condition, where the base can never equal 1. So taking 1 on the left hand side, we get this, and then let's factor the quadratic equation. This gives two values that x cannot be, which is half and 6 by 5. And now comes the final computation to find the intersection. Let's find the intersection of condition 1 and condition 2 using a visual number line scan. The first condition says x is less than 1 by 9 and greater than half. Second condition says x is either less than 7 by 10 or greater than 1. Now if I compare, obviously 1 by 9 is 0.11 approx and 7 by 10 is exactly 0.7. So on the number line, 1 by 9 comes before 7 by 10, but between them half, which is 0.5, comes, and we have 1 at last. You can already see the intervals included in condition 1 and condition 2 marked in the diagram. Now the common regions are clearly minus infinity to 1 by 9 and 1 by 2 to 7 by 10 and 1 to infinity. Now let's factor in our base unity condition. X not equal to half is already naturally excluded because the middle interval uses open bracket at half. But x equal to 6 by 5, which means 1.2, and that falls directly inside our interval 1 to infinity. So therefore it must be explicitly subtracted. So this is our final domain. Now let's compare this precisely with the questions format. We get the values of a, b, c, d and e. Now the problem asks for the value of 90 into a plus b plus c plus d plus e. Then we multiply 90 across each term inside the brackets directly to bypass finding a common denominator. And adding them, we get the value 316. Option C, 316 is a flawless victory. Never let busy algebraic intervals distract you from the basic core properties of log bases. If you unmasked the 6 by 5 exception during our opening knowledge check, drop a thunder in the comments below, subscribe to Think Sharp Alley, and let's tackle question 21.